Hi everyone, you're watching the 11th lecture of EE635 Applied Linear Algebra. This would be the third and final module. Okay, so in the first two modules, we have set up this problem of diagonalizing a linear operator or a matrix, which originated from the problem of trying to solve coupled system of ordinary linear differential equations. Okay, and then we realize that this diagonalization is possible if there are n linearly independent eigenvectors. Eigenvectors are special vectors of linear operators, which are such that the action of the linear operator on this vector is just manifested by a scalar multiplication of the vector. They are special vectors, they are eigenvectors, and the scaling also is special. They are called eigenvalues, and we've seen that we can figure out these eigenvalues by finding out what is known as this characteristic polynomial of corresponding to the linear operator and its roots. So a number is an eigenvalue of an operator if and only if it's a root of the corresponding characteristic polynomial. We have seen that this characteristic polynomial can be found out by taking the determinant of this matrix Si minus A, where S is a placeholder, is a variable, and A is any matrix representation of the linear operator. Right? Now the question that we faced was when can we guarantee existence of n linearly independent eigenvectors? We saw in the last module that one such guarantee can be given in terms of these eigenvalues. So if n is the size of the matrix, or equivalently the dimension of the vector space where things are happening, if there are n distinct eigenvalues, then there's a guarantee of existence of n linearly independent eigenvectors. Yeah, we did a proof of this by a lemma which we proved by induction. So n linearly independent distinct eigenvalues gives rise to n linearly independent eigenvectors. However, the question is this all? Is this also necessary, in the sense that if I have n linearly independent eigenvectors, does that mean I have n distinct eigenvalues? The answer is no. Yeah, in general, to have n linearly independent eigenvectors, I do not necessarily have to have n distinct eigenvalues. So what is it? What is the property of the matrix or the linear operator that guarantees n linearly independent eigenvectors? N distinct eigenvalues is only sufficient. It's not necessary. Could there be something more? Yeah. So in this module, we'll answer this this question. We'll give a complete answer to this question, that when does an operator A admit n linearly independent eigenvectors? Okay. So without further ado, let me share my screen. And let's get going. Yeah, here we are. So we have started looking into this idea called geometric and algebraic multiplicities, right? So if we have characteristic polynomial chi s, okay, and suppose that chi s factorizes as dot 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 up to s minus lambda k dk. This is the characteristic polynomial, and these lambdas are distinct, suppose. Yeah, then of course d1 plus d2 plus dot 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 plus dk is equal to n. Yeah, and di is called the algebraic multiplicity of lambda I, and dimension of the null space of lambda I minus A is called the geometric multiplicity of lambda I. Yeah. Now we have noticed that okay. So let us repeat. So suppose A is such that, so suppose A is such that under a basis A basis B, A represented by B, which you know could be just T inverse AT, is lambda, which looks like lambda 1. Okay, let me write it down like, okay, lambda 1, then lambda 2, and so on, lambda n, lambda k, like this, yeah, which is the same as writing this down as lambda 1 into identity of some size, in fact size d1, lambda 2 into identity of size d2, and so on up to lambda k into identity of size dk. If it is like this, then the characteristic polynomial here is indeed s minus lambda 1 whole to the power d1 dot up to s minus lambda k whole to the power dk. Yeah, and d1 plus d2 plus dot plus dk is equal to n. And further, notice the following, that in this case, so if I look at lambda I minus a, lambda I into identity minus a, look at this operator and look at its representation. Its representation is going to be indeed lambda I into identity of size n minus this lambda matrix. Yeah, notice that the rank of this matrix is precisely equal to n minus di. Yeah, and therefore dimension of kernel of lambda I minus this is equal to dimension of lambda I minus a, which is equal to di by rank nullity theorem. Okay, now these spaces will be special for us. You see, dimension of kernel. Yeah, these spaces will be special for us. We are going to define Wi as the kernel of lambda I. Do this as an immediate attention problem. Show that this Wi is isomorphic to lambda I identity minus a. Yeah, do a matrix representation of that. This is a matrix. Look at kernel of this, and then show that Wi is in fact isomorphic to this one. This is without taking any basis or anything. This is in general. This is a subspace of V. This of course is a subspace of f to the n. Show that there's a one-to-one correspondence between this subspace, I mean isomorphism between this and this subspace. Yeah, this you do as a part of your immediate attention problem. In fact, it's very simple. Follows immediately from the isomorphism between V and f to the n. Yeah, the coordinate representation idea. Well, so with that, it then follows that so let me write this statement then. So if A is indeed diagonalizable, then chi AS has the form s minus lambda 1 to the power d1 dot 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 up to s minus lambda k to the power dk, lambda I not equal to lambda j if I is not, so that means these lambda 1 up to lambda k are distinct eigenvalues, and d1 plus dot 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 up to dk is n with the property that di is equal to the dimension of the space wi. This is the property when we have geometric multiplicity is equal to, this is a property we call, this one is called geometric multiplicity is equal to algebraic multiplicity of for all the eigenvalues. So dim wi is the geometric multiplicity, and that is equal to the algebraic multiplicity, right? Because you see, if it's diagonalizable, then you will have a diagonal representation like this. Yeah, so this immediately follows. And now if I find out the kernels of this lambda I minus a, those kernels by this isomorphism property, they will be isomorphic to these kernels, and these kernels, the rank calculation tells us that when I do lambda 1 identity minus this capital lambda matrix, that has rank equal to n minus d1, so nullity is d1. Lambda 2 identity minus capital lambda, that is this matrix, is rank n minus d2, so therefore nullity is d2, and so on. So the nullities are in fact given by these di numbers. Yeah, I hope it's understandable. All of it follows from the structure of the matrix capital lambda. Yeah, I hope it's understandable. If it's not, please let me know. Okay, now moving on. We need to notice something very interesting about these wi spaces, right, in order to proceed any further. In fact, we'll see that this condition that I've written here, no, this one, this one, this one, all these conditions, that actually is necessary and sufficient for diagonalizability, right? But let us try and see why should this be true. For that, we have to analyze these wi spaces in much more detail. So first property that I want you guys to notice is that every vector in wi, so v in wi means v belongs to kernel lambda identity minus a. This implies lambda I minus a acting on v is equal to 0. This of course implies av equals lambda I v. That means it's an eigenvector, every non-zero vector. On the other hand, if this is true, then this implies this is true, this implies this is true. and this implies, of course, this is true. So this is in fact an if and only if statement. So that means every vector in these Wi's are eigenvectors. Wi contains all eigenvectors corresponding to eigenvalue lambda I. Okay. Now let Bi be a basis for Wi, right? We have the following lemma. Remember, these lambda i's are distinct, yeah? The lemma says that B1 union B2 union dot 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 union Bk is a basis for W defined as W1 sum W2 sum dot 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 up to Wk. So these are all eigenvectors corresponding to eigenvalue lambda 1, eigenvectors corresponding to eigenvalue lambda 2 dot 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 up to eigenvectors corresponding to eigenvalue lambda k. Sum those things up, you get a vector space, I mean subspace of V. Yeah, of course, this is a subspace of V. Yeah. Point is that this union is a basis for this. Yeah. Proof. How do we do the proof? Well, first thing that we notice is that this union, no, let me write it in shorthand. Union I going from 1 to k, Bi is clearly a generating set for W, of course, no, because how do vectors in W look like? That's a linear combination of vectors, not linear, not even linear combination. That's a sum of vectors from W1, W2 up to Wk. Now W1 can be written as a linear combination of vectors from B1. Any vector from W2 can be written as a linear combination of B2, so on up to Bk. So therefore, any vector in W can be written as a linear combination of things from B1, B2 and up to Bk. So in fact, this union must be a generating set, right? So this is trivial. What we need to show is that this set, no, this union is in fact linearly independent. Yeah? Let us see why should this be true. Now, so let us say Bi is defined as, Bi is composed of say Vi1, Vi2 dot 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 up to Vi Di. Yeah, these are the vectors, and this is for I equal to 1 up to k, right? So now, so look at this linear combination. Yeah, so let us look at a typical linear combination. Typical linear combination of vectors from this union is given by alpha 11 V11 plus alpha 12 V12 plus dot 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 plus alpha 1 D1 V1 D1. Yeah, this is a linear combination of vectors from B1 plus alpha 21 V21 alpha 22 V22 plus dot 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 plus alpha 2 D2 V2 D2, right, plus dot 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 plus alpha k1 vk1 plus alpha k2 vk2 plus dot 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 plus alpha k dk vk dk, and suppose this is equal to 0. Yeah, is that all right? Now I look at this guy and suppose I call it, say, call it w1 plus w2 plus dot 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 up to wk. This is equal to 0, where wi is defined as summation alpha I j going from 1 to di vi j, like this. Yeah? This is how we have defined for I equals 1 to k. This is what these w's are. Notice that this is a linear combination of vectors from bi. So of course this is a vector in wi, which means wi is an eigenvector with eigenvalue lambda I, and this linear combination goes to 0. Does that tell you something? I say this implies w1 must be 0, w2 must be 0, so on up to wk must be 0. Why? Because indeed these are eigenvectors, no? Yeah, if they're 0, then fine. If they're non-zero, then they're non-zero eigenvectors. Now suppose some of them is 0, not all of them is not all of them is 0, some of them is non-zero, let's say. Yeah, some of these guys are non-zero. So indeed if some are non-zero, then that gives a non-trivial linear combination of eigenvectors corresponding to distinct eigenvalues non-trivial linear combination of eigenvectors corresponding to distinct eigenvalues that goes to 0, but that is contradictory to the fact that this contradicts lemma from module number 2. In module number 2 we have actually proven that if there are distinct eigenvalues, then corresponding eigenvectors are linearly independent. Yeah, so if there are non-zero eigenvectors here, these are eigenvectors. Yeah, if they're non-zero, then they're eigenvectors. If they're 0, then 0. If they're non-zero, then even if some of them are even if some of them are non-zero, some may be 0, fine, but suppose some of them are non-zero, then those non-zero vectors give me a non-trivial linear combination. It's like, let's say everything is 0, but w1 and w2 are non-zero, then I have w1 plus w2 going to 0. That's a non-trivial linear combination of this w1 w2 two eigenvectors which correspond to distinct eigenvalues lambda 1 and lambda 2, right? Which is contradictory. So therefore all of them must be 0. Then and only then is that possible. But now if all of them is 0, so suppose w1 is equal to 0, suppose w1 is equal to 0, this implies this linear combination alpha 1 j going from 1 to d1 v1j, this is equal to 0, but then this means alpha 1j is equal to 0 for all j, because v1j, this set j going from 1 to d1, this set is linearly independent by definition. This is bi, this is b1. So all these vectors are linearly independent, so these coefficients must be 0. And similarly W2 equal to 0 implies alpha 2j is equal to 0 for all j, and so on up to Wk equal to 0 implies alpha k j equals 0 for all j. That's it. That means all the coefficients are 0, which means alpha ij is equal to 0 for all I equals 1 to k and j equals 1 to di. 1 to di. This is equal to 0. So these coefficients are 0. This means union I going from 1 to, what is it, 1 to k, bi is linearly independent. Yeah, is it all right? Okay. One more point that I need to mention here is that, I have here for this lemma to work, for this lemma to work, these di's, these dimensions, no dimensions. So this is very important to notice. Yeah. So let me switch on my video. This is very important for us to know. So for this lemma to work, the dimension of these W1, W2 up to Wk, they need not match the dimension, the numbers corresponding to the algebraic multiplicities. These numbers are anything. Yeah. So whatever these numbers are, let's say these numbers are R1, so dimensions are R1 up to Rk, right? So I think that's better. So instead of D, let me replace them by R, because we have to understand that this doesn't have to match the D's here, the D's that correspond to the algebraic multiplicities. Yeah. The proof is independent of that fact. Right. So let me just substitute these guys by numbers R. Okay. R I, R1, R1, R2, R2, RK, RK, RI, RI, RI. This is R1 in fact. R1, RI. Yeah. So the point is, I have created these subspaces Wi, which can contain the eigenvectors. So this is kernel, the null space of lambda I identity minus A. Yeah. And they have basis Bi. Okay. Then I look at this, I create this sum of these eigenvector spaces, right? Then this has basis given by B1, B2 union Bk. This is a basis. That's the idea. That's what the lemma says. Whatever be these dimensions, I don't care. As long as I have these spaces W1 up to Wk, and then I form this W, then this W will have a basis given by this union. The reason is that it's a generating set by default, I mean, trivially, and also the fact that B1, this union contains vectors which are linearly independent. Now let us see what happens. Yeah. Theorem. So the premise remains the same. V is a vector space over a field F. A is an operator, is a linear operator, then the following are equivalent. Then the following statements are in fact equivalent. What are they? Number one, A is diagonalizable. Number two, chi A S looks like S minus lambda 1 to the power d1 dot S minus lambda k to the power dk. Lambda I not equal to lambda j for all I not equal to j. That means these are distinct eigenvalues. W I defined as kernel of lambda I minus a. Then dimension of Wi is equal to di. This is number two statement. Number three statement is right. Yeah, right. V has n. Okay, here also dimension of V equals n less than infinity. It's a finite dimensional. Yeah, V has n dimension of V equals n less than infinity. V has okay, V has dimension n. V has n linearly independent eigen vectors. Yeah, proof now. So these are equivalent. Yeah, so I have an equivalent condition, necessary and sufficient condition for diagonalizability now, which says that this is the characteristic polynomial, how it's going to look, and algebraic multiplicity will be equal to geometric multiplicity for all the eigenvalues, right? Now, how do we prove this? These three arguments that they are equivalent. So one implies two is something that we have already discussed. You see, if A is diagonalizable, then A will have A uh, A can be represented. There exists a basis where A is given by that lambda 1 d1 and so on. So this part of the proof. So A admits representation by lambda, which is lambda 1 I d1 dot up to lambda k I dk for some d1 up to dk. And this implies chi a s equals chi lambda s, which is s minus lambda 1 to the power d1 dot up to s minus lambda k to the power dk for some d1 up to dk. I don't care, you know, these numbers. Yeah, so this is what this characteristic polynomial is going to look like. What we have to prove? Yeah, of course, lambda I not equal to lambda j. We can already assume that. That is how we have formed this. You know, diagonalize and then club those eigenvalues together. Okay, and from here also, by your immediate attention problem, also follows that Wi defined as kernel null space of lambda I identity minus a, then dimension by immediate attention problem, this dimension is equal to dimension of kernel of, it's going to look like lambda I minus lambda 1 into ID1, like this. Lambda I minus lambda n into lambda k into idk. In between there will be a 0 of size idi, right, which is the same as this kernel will be from rank nullity theorem n minus the rank, which is n minus di. This is going to be di, right? So 1 implies 2 is trivial, 2 implies 3 is what the lemma says. Yeah, this is interesting. Now 2 is like this, right? So then if I define W as summation of W1 plus dot 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 WK by lemma B1 union up to BK is a basis for W, but what is the size of B1? How many vectors? D1, because D1 is the dimension of W1. So the basis must have that size. BK must be equal to DK, right? Therefore, this union, which contain all linearly independent vectors, this whole thing contains all linearly independent vectors. So then this thing must have size equal to D1 plus D2 plus dot 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 up to DK, right? But then these numbers are the algebraic multiplicities, no? So this is equal to n. Yeah, this follows from 2, from the statement 2. These d1s up to dk's are the algebraic multiplicities, so they sum up to sorry, so they sum up to the number n, right? So then dimension of W is equal to n, but W was a subspace of V which has dimension n, so therefore dimension W must be less than or equal to dimension V, which itself is n. So the two dimensions match, which then means that W must be equal to V, which means V is given by W1 plus dot dot WK. But these are what? These are eigenvectors. Yeah. And so these bases, no, B1 up to, they contain the eigenvectors only. And this forms a basis. So B1 union BK is a basis for V, but these guys contain only eigenvectors. So therefore this means there exist n linearly independent eigenvectors. So 2 implies 3, and of course we have already seen that 3 implies 1, because if there are n linearly independent eigenvectors, then of course it's diagonalizable. So that's the proof. Yeah, so this is what it is. This is when it becomes diagonalizable. So of course the natural question that now comes up is that when is it not diagonalizable? Because it's a necessary and sufficient condition. I know that the moment we have any of these conditions are violated, then there will be it's not going to be diagonalizable. So this goes to you as an immediate attention problem. Come up with examples of matrices where algebraic multiplicity is not equal to geometric multiplicity. and convince yourselves that that is the situation when the matrix will not be diagonalizable. Yeah, is that all right? Okay, then. So with this problem in mind, we will now see the situation. We'll see in more details the situation when this is not going to be diagonalizable. We'll see what else can we do. If the matrix is not diagonalizable, then what is it that we can do? Yeah, that will force us to investigate this situation further, and we'll see that the next best thing that we can expect when it's not diagonalizable, the next best thing to expect is to look for block diagonalization. Yeah, instead of the whole matrix to be diagonal, it will be blocks of matrices. It will be a diagonal matrix of blocks, and each block may not be diagonal itself but may have some different structure. Yeah, and based on that, we will see the Jordan canonical form and the rational canonical form. But unfortunately, to go to this Jordan canonical form and rational canonical form, we'll have to build up a lot of machinery. Yeah. Principal among these machineries would be the ideas coming from polynomials. Yeah, polynomials, their GCDs, Bezout identity, and things like that. Seems like completely disconnected things, but I will see that they indeed are connected, and that will be the subject matter of lecture number 12. Okay, so that will be uploaded sometime next week. So till then, bye for now, but I urge you to please attend the video uh, the the video session, the live video sessions. Also keep watching the video lectures. If you have any doubts, please let us know. You have various different fora to voice your opinion, your doubts. Okay, and by the way, these things in a slightly different form will be available in chapter number 6 of Hoffman and Kunze. Okay, then, so till we meet for the live session and in the next video lecture. Till then, bye bye, take care, stay safe, stay healthy.